Continuing through the content of electric potential and also electric potential energy, we're at 3.2. And this is for Physics 131 students, and this is how to calculate voltage on a continuum of charges. So a bunch of protons built up onto a line of charge, or a bunch of electrons on a line, or a surface area, or a ring, things like that. So to begin with, make sure you do the reading, Untitled Chapter 18. So if you're in Physics 112, well, actually Physics 131, Untitled Chapter 18. If you're doing OpenStax, it'll be Chapter 7. All right, and this is going to go with our homework number 5 in electric potential. And I believe it's the last two problems that are electric potential problems on a continuous distribution. Okay. So here's our strategy. What we're going to do is kind of identify a point P away from the distribution of charges. We're going to try to draw the distribution of charges. And then we're going to take a small chunk of those charges and call that delta Q. Okay. And then we're going to identify the dimensions of that delta Q. Okay. If it's a line of charge, it'll just be varying along a line. If it's a two-dimensional surface, it'll have two dimensionals, like an X and a Y direction, or even a theta. So that's what we're going to do. So then we're going to identify the charge density of that, and then move on to actually integrate over that charge density. All right. So the best thing to do is maybe just to jump right in. So again, for discrete charges, you're just summing up all the individual charges. But what happens if you have a huge distribution of charges? So much charges, billions and billions of charges. Well, calculating each discrete charge is not going to be the best strategy to solve this. Okay, so what we're going to use is we're actually going to calculate along the continuum of charges using the charge density, lambda or sigma or rho. Okay, so our first problem is you have a bunch of charges built up along a length of line. Okay, and what we're going to do is the first thing that we're going to do is we need to calculate the voltage at this point, a distance x away from that at the center of that line. So what we're going to do is we're going to identify the charge density using dq, and then we're going to go ahead and define the voltage at that point. All right. So what I'm going to do is I'm going to go ahead and mark up this document. So I'm going to go ahead and begin drawing on this document. I'm going to mark it up. So I'm going to hit my comments, and then I'm going to close that out. And then I'm going to use a pencil to do this. Okay, so let's go ahead and identify a small chunk of charge. Okay, and that is our dq. Okay, and how are the charges varying along this length? Well, they're varying only in one dimension, and that is going to be delta y. Okay, so all the charges are varying along this length, which is in the y direction. So we're going to use y as our variable. Okay, now let's go ahead and identify the charge density. Okay, so charge density is, so since it's a line, is just going to be, it's going to be lambda. And that's the number of charges built up on here. And in this case, if we were to actually count this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 Qs built up. And let me change that, make it a better looking Q. We have 16 Qs built up along that length L. Okay. Well, really, this is a continuum of charges varying along a vertical axis, so delta y, and that's how we've kind of identified that. Okay. Well, over here, so this is our basic equation, and then in this case we could actually use just this part to solve for what dq is, which we'll do here in a second. So let's go ahead and write our base equation for the voltage. So the voltage, or electric potential, is equal to K dq all over R squared. Okay. So let's go ahead and do a couple things here. So we have the electric constant, we have dq, and this is our dq, and we could solve for dq using this, and we have to find out the distance away. So our dq that we've identified is a distance away, that is r away from our point. Well, this dq, and I'm going to call this a distance y. This is a distance y up, and it's distance x horizontally from where we're calculating what the voltage is at this point. To solve for r, we're going to use the Pythagorean Theorem, which is equal to c squared equals a squared plus b squared. So that's equal to x squared, square root of x squared plus y squared. Okay. Now we need to substitute in dq. Now I could use the 16q over L, but lambda is equal to 16q over L. So what we could do is we're just going to say dq, and we're going to multiply lambda times dy, and we get lambda dy. We have to multiply both sides by dy to get what dq is equal to. So dq here in our equation is equal to lambda dy, where lambda is equal to 16q over L. Okay? And then we also know that r is equal to, and that should, I'm sorry, I put a squared on the bottom. That would have been the electric field. I'm sorry about that. That should just be r. Made a mistake. Awesome. And so this is just r on the bottom. Just to be consistent, we're basically doing this. And so that should just be r, and r is equal to x squared plus square root of x squared plus y squared. So I'm going to substitute in k, and our dq is now going to be lambda dy over r, which is x squared plus y squared square root. Let's go ahead and take this a little bit further. Okay, so this is our base equation. All right, and if we're going to solve for this, we're going to have to integrate both sides. We're going to have to integrate the dV by the initial voltage to the final voltage across all of these voltage. All of these guys are creating a voltage at this point right here, and that's going to be equal to the integral of this side. So that's going to be we're going to integrate. We have to integrate both sides, and we're going to integrate from negative L over 2 to L over 2. Okay, and that's going to be k lambda dy all over x squared plus y squared. Okay. Well, what this is going to yield is we're going to have a delta V, V final minus V initial on this side. And let's think about this for a second to simplify this problem. Okay, K and lambda are constants. Okay, So really, see this positive, these positives, they're all going to increase the voltage here. And what we could also say is that these positives here aren't going to subtract from that, because that is thinking about it with vectors. They're also going to be increasing the voltage here. So this side is a mirror image, is the same thing as this side. It's just going to double up the voltage that this side is going to do. So what we could do is I'm going to pull my constants out, k and lambda, and I'm going to write my integrals, but we're going to do something to simplify the problem so that we could actually get a nice clean setup for our integral. Okay, if we just go ahead and just integrate it from 0 to L over 2, just integrate the top side. Well, the bottom side is also just going to add to the voltage, right? So if we just integrate the top side, the bottom side is just going to double up on top of that. So we're just going to multiply this by 2 and thus integrate both sides and simplify this. All right? So this is how you begin this voltage problem, okay? So this is getting, so obviously we're running out of room. So what I want to do is I want to move to Microsoft Whiteboard, okay? And I'm going to copy this base equation to that, okay? So I'm going to copy it just as it appears, okay? And we're going to have delta V, which is V final minus V initial, and that's going to be equal to 2k times lambda, and that's going to be from 0 to L over 2, and that's a positive L over 2. And I believe we had our values as dy over square root of x squared plus y squared. Well, this is a deceptively tricky integral. It really looks simple. It ends up being a whole deal. And if you want to go ahead and skip on to the solution to this, it ends up just becoming right here. I don't know why that is there, but it ends up becoming just this right here. The natural log of x plus x squared plus, in our case, it will be the natural log of y plus the square root of y squared plus x, and going from 0 to L over 2, and this would be 2k lambda in the front, okay? This problem, they're only doing 1/2 a wire. We're doing both halves, so we're going to be multiplying both sides by, we're going to be multiplying by 2 here. But that's going to end up becoming the natural log of x, of y plus y squared plus x squared to the 1/2 power. So the square root of y squared plus s squared, and it'll be the natural log, okay? So that's a quick and easy solution to this, but I want to show you how they get this, all right? So we're going to have to do some substitutions and some tricky tricks, okay? So one of the things that we're going to do is we're going to just go ahead and define y. Let's go ahead and define the tangent of our triangle, okay? And I'm going to draw our triangle over here. And if you remember, I identified a little chunk up here on our wire, and that was our DQ. Our DQ right here. Come on. Let me zoom out a little bit. I'm not sure why it's not allowing me to write a little Q there. There we go. So that was our little chunk that we identified. I'm going to zoom back in on that. And believe me, I'm going to need as much room as I can. And we identified this as y, This is x. We're going to use theta to be this, and this was the square root. It was r, which was the square root of x squared plus y squared. Okay? So that's our little triangle, and we're going to need this to actually do this integral. So what we could say right here is that the tangent of theta is y divided by x. Okay? So y divided by x, right? Which means that y is equal to x times the tangent of theta. Okay? Let's square both sides, and I'm building up to something because I'm going to have to work with this. I'm going to have to do some substitution to massage this into something that I could actually integrate. Okay, so y squared is going to be equal to x squared tangent of theta. Well, tangent squared of theta. Okay? And what we're also going to need is this, is that there's an identity, a trig identity, is that tangent squared of theta is going to be equal to 1 plus the secant squared of theta. Okay? So we're going to need these two to help us with this. So I'm going to begin substituting these two things in, and eventually I'm going to have to differentiate y is equal to x plus x tangent of theta. Whoops. So let's go ahead and do that right now. Okay. So I'm going to now continue writing this right here. So delta v is equal to 2k lambda from 0 to L over 2. Okay. I'm going to leave dy there, and I'm going to start substituting in this stuff right here. Okay. So dy is going to be equal to square root x squared plus y squared is now x squared plus tangent squared of theta. X squared plus tangent, not plus, it's just x squared tangent squared of theta. X squared tangent squared of theta. Okay. I'm going to keep copying all these integrals over. 0 to L over 2. Okay. Now we have x squared plus x squared tangent squared of theta. So I'm going to go dy, and I'm going to substitute out that x squared. Okay. So I'm going to substitute out x squared, and what I have now is 1 plus tangent squared of theta. Still dy. We're gonna substitute that in a second. Okay. Well, now we could see that we're gonna need to do some things right here. And I just realized I made a mistake up here. This is supposed to be the identity was actually tangent squared of theta plus 1 equals secant squared of theta. Can't believe I did that. I am so sorry. I'm making mistakes all over the place. I hope you'll learn from my mistakes. So we now know that this right here is 1 plus tangent squared of theta. Well, tangent squared of theta, and that is not very good looking square here. Okay. Tangent squared of theta, tangent squared of theta plus 1 is secant squared of theta. Well, I could substitute that in here. 2k delta y, 2k lambda from 0 to L over 2, dy square root x squared secant squared of theta. Okay, well now I could bring this out of the solution. Delta V equals 2k lambda 0 to L over 2 dy and x squared secant squared theta inside this square root is just going to be x secant of theta. Okay? Now we're going to have to do, now we have a differential of y, but we have this problem right here. This is actually varying along a theta. So we're going to further reduce this. So let's do this. So what I'm going to do is I'm going to go ahead and copy this. I'm going to copy this down here. And we need to substitute in some, we need to find this in terms of thetas. Okay? And I'm not sure what we're going to get here. Tangent of theta. Okay? And I'm going to differentiate dy with respect to theta. So, oops, got our eraser there. So this is y, so we're going to go differential of this, tangent of theta, d theta. And what we'll get is dy d theta is going to be equal to x is a constant, and the differential of tangent of theta is secant squared of theta. And that's equal to dy d theta. Okay? Right? So I'm going to multiply both sides by a d theta. And what I get is, let me do something real. I don't like that I put, oops, let's go ahead and, I want to go ahead and make this equal to this. And what I get is, I'm going to solve for dy. dy is going to be equal to x secant squared of theta d theta. Okay? So I am going to plug d theta, dy, this x secant squared, I plug this right into this right here. Okay? Excuse me. So now the voltage, the change in voltage, is 2k lambda from 0 to L over 2. And dy is now going to be x secant squared of theta d theta all over x secant of theta. All right? The x's will cancel out. X's will cancel out. This secant of theta will cancel out with the square at the top. And what this ends up becoming is something that's pretty neat. It's going to be 0 to L over 2. Whoops, I forgot my constants in the front. So I'm going to need a little bit of room here. I'm going to put 2k lambda from 0 to L over 2. And that is going to be secant of theta d theta. Okay? Now, you could go look this up. I think the CRC has what this integral is as a quick lookup. This is kind of a complicated, U substitution, and it begins like this. So I am going to do the whole thing. 2k lambda 0 L over 2. So we're not done. We have to finish this integral. Okay, and to set up the U substitution, I'm going to do this. Secant of theta right there. I'm going to multiply secant, I'm going to multiply this secant of theta plus tangent of theta all over secant of theta plus tangent of theta. And I need to use this to set up my U substitution. So this is looking a little weird, but here we go. So I'm going to multiply this out over here. So delta V is going to be equal to, I'm going to multiply, well, I'm going to copy our constants through 0 to L over 2. Okay. Secant of theta times secant of theta plus tangent of theta is going to be secant squared of theta plus tangent of theta secant of theta all over secant of theta plus tangent of theta d theta. Okay? So here's the part that we're going to have to start doing U substitution. Okay? So U substitution for this guy is going to be, what I'm going to do is I'm going to select that U substitution is going to be equal to this. Secant of theta plus tangent of theta. So I'm actually going to make it equal to what I put on top here. And it's a kind of a trick I learned a long time ago by my old Calc 3 instructor, well, Calc 2 instructor. He was a nice fella. So I'm going to differentiate both sides of this, okay? And basically, just to finally get to this, what we're going to get is we're going to get secant of theta, tangent of theta, plus secant squared of theta, d theta. Okay, I don't want to go through this whole thing that we just did up here. Secant of theta becomes the differential of secant of theta is secant theta tangent of theta, and the differential of tangent of theta is secant squared of theta, and then the du d theta is what we were doing. So this is what du is equal to. All right. Well, I'm going to substitute these two guys, u and du, into our equation. So I started to write my equation here, but you can't really use the same limits that you used before. Okay. So this, by changing this, by substituting this stuff in here, it actually becomes a slightly different equation. So basically what I'm doing is I'm integrating this. So I'm going to plug in for secant squared of theta plus tangent of theta secant of theta, that is this part, that is just du, and times d theta, that is just du, right? And secant of theta plus tangent of theta is just u. So when you integrate this, basically what you get is you get the natural log of u, u plus c. Well, we're going to go ahead and use this. So we can now use this, right? So we've got, and I moved that a little too high. Let's go ahead and put that there. I'm going to bring this down a little bit. In fact, I'm going to see if I can scroll this down a squidge. But I think I could just clean it up using this and keep it there. But anyways, well, we now know what the integral of this is, right? So delta V Okay, so if I allowed this to pop back out, now substituted in my u for here, we'd have the natural log of u, which is secant of theta plus tangent of theta, right? Plus c, right? And that should be plus c. Well, let's go ahead and use that. Now what we know that this is 2k lambda times the natural log of secant of theta plus tangent of theta. Oops. Tangent of theta. It thought it was a triangle. Tangent of theta. And we're going to integrate that from 0 to L over 2. Okay? Well, that looks pretty... I don't know what to do with that, really. This is a distance, and we have thetas here. So we have to use our triangle again, and then go ahead and substitute in our sides for our triangle. Okay? So I'm going to do a couple things off to the side. Again, I'm going to rewrite that tangent of theta is equal to y over x, and secant of theta, which is equal to 1 over cosine of theta. Well, cosine of theta is adjacent over hypotenuse. So the secant of theta will be the opposite of that. That'll be hypotenuse over adjacent. Okay? So we're going to substitute these two guys into here. And I will need some room. So I'm going to scooch this down a squidge. Okay. And now I'm going to go back up. I'm going to copy my delta V. And that's equal to 2k lambda. And we're going to have a natural log here. And the natural log is going to be, now secant, we said, is square root of x squared plus y squared over x. And tangent is going to be y over x. From 0 to L over 2. I'm going to clean this up a little bit so we have a nice little solution here. Okay? So what that becomes is delta V equals 2k lambda, multiply that by the natural log, and this is a common variable of x, so that's going to be the natural log of the square root of x squared plus y squared plus y all over x from 0 to L over 2. Okay? And I don't know why I put this in here. I could have just put in equal sign. So this is equal to this, right? Now if I wanted to, I could go ahead and plug my L over 2 into here, and you would see the solution, and I guess I could go ahead and do that right here. So we get the final solution. Might as well finish it. Natural log, and I'm giving myself a lot more room here, square root, and x squared is distance, y squared is going to be, y is going to be L over 2 in here, so this is going to be x squared plus L over 2. Come on, don't do that. L over 2 squared plus y, which is L over 2, divided by x. And so this is our ultimate solution to this. Okay? It's our ultimate solution around this guy. Okay? Well, if you look at this, this is actually the same solution that they got here. Okay? Except they were using it from 0 to L, and they're only using 1/2 of a line, so they're calling this 0 to L. And that's L plus the square root of L squared plus D squared over D. So these two solutions are the same thing. Now, I'm not expecting you guys to go through all of this, right? A lot of physics professors will just say, something just disappeared. Okay. A lot of physics professors would just say, okay, you've gotten this, you've got to this point, right? Basically recognizing that if you could get that this solution right here, a lot of physics professors, and you'll see in the supplementary videos, just go ahead and start writing this, essentially. Okay? So it's up to you, but this is a lot of work just to get to this. So I would accept if you wrote this as your differential, not doing all this and just going right to this. So please use your course notes when you're doing this problem in your homeworks. Okay. So now we're going to move on to electric potential for a ring. So now we have a continuous line of charge around a ring. Okay? So let's go ahead and mark up this document like we're doing before with the line of charge. So just like before, we're going to go ahead and we're going to imagine there's a line of charges all built up along this ring. And so this is a ring, and the center of the ring is the 0 point. The radius of this ring is A, and we're going to try to get the voltage at a point P, a distance x away from the center of this ring. And as you can see, the triangle is already made for us. The distance to this point right here is r equals x squared plus a squared. Now, to do this integral, we're going to have to identify some charge. So we're going to identify some charge here, okay? And this is a continuum of charge, okay? And we're going to go ahead and identify this right here. So this continuum of charges is changing along this entire length, which is 2 pi times the radius. So it's changing along the circumference of this ring, okay? And it's changing along dq, okay? Along d theta, okay? So we're going to call this whole ring as theta, all right? And so this is a line of charge. To do this, we're going to have to go ahead and identify a line of charge. And again, this line of charge has a buildup of q's along the entire length. Well, in this case, I haven't listed how many q's are on here, but we'll just call it a bunch of q's, and we'll just call that q, right? Well, this length is 2 pi times the radius, and the radius is a, okay? Well, our differential then is dq, so that thing is changing, that d theta is changing, okay? And the length now is just going to be the radius d theta, okay? So solving for this, I'm going to solve for dq using this part right here, okay? And if you notice, the a's are going to cancel out, and what I'll get is q over 2 pi equals dq d theta. And so dq is going to be equal to q over 2 pi d theta. Okay? So I hope that's readable. This is a q, and this is a theta, and this is a 2 pi. Well, to do this, let's write our basic integral. dv is equal to k dq over r, and we're going to integrate both of these, this from vi to vf, this from k dq over r. Let's go ahead and plug in our, before we evaluate the limits, let's go ahead and plug in our variables, okay? So actually, let's go ahead and evaluate our limits. Well, this is going from 0 and is going all the way, to 360 degrees, which is 2 pi. So this is varying from 0 to 2 pi, and we're going to evaluate d theta as 360 degrees as usual. Okay, so now our d theta is varying. We have k dq, which we're not using lambda in this case. Lambda is so now dq is going to be equal to q over 2 pi times d theta. Q over 2 pi d theta. Okay? And r is going to be the straight line distance from where we've cited in our integral, our dq, all the way to our point P. And that's going to be the square root of a squared plus x squared. Okay? And if you notice, this distance isn't changing no matter where you, so from here to here is also x squared plus a squared. So in a weird way, not in a not so weird way, this thing right here, in fact, this whole part, and I'll highlight it red, this whole part is a constant. And really, the only thing that is changing here is d theta, because we're going around the entire circle. Okay? So dv is varying from is integrating from vi to vf, and that is actually just going to be vf minus vi, which we're calling delta v. And all of this is a constant, so I'm going to call that k, q, and let's write it better than I am writing it here. kq over 2 pi square root a squared plus x squared, because that is a constant. And so now comes our integral, 0 to 2 pi d theta. Okay? Again, this entire thing is a constant. Well, if you integrate from 0 to 2 pi along d theta, all you get is basically 2 pi minus, you get 2 pi minus 0, which is just 2 pi. So really, we're getting 2 pi square root a squared plus x squared, and that is going to be 2 pi minus 0, which is what that integral is, which 2 pi minus 0 is just 2 pi, and 2 pi divided by 2 pi is going to, so that is going to cancel out. So this 2 pi is going to cancel out with this entire part right there. And essentially what we're going to be left with is just this, kq over square root a squared, which is the radius, plus x squared. Okay? And that's how to get the electric potential of a ring of charge. I think there's also a lecture tutorial about this too, so please try that when we're done. Cool. Let's move on to the next problem. Oh, by the way, here's some supplementary material from Knight on a ring of charge. So here we have a disk of charge. And so we're going to use the same method that we just did before, except now we're going to approach it for a disk of charge. So let's have you guys go ahead and try this, okay? So try using the method that we just did before. Go ahead and pause the video and try this out, okay? All right, we're back. Let's go ahead and try to define what dq is. So sigma is equal to q over the area, right? It's a two-dimensional density, okay? And what that means is that dq is varying along this small r, right? And it's varying along this small r, and we also are going around. So that area has got two dimensions. It's got a circular dimension, which is 2 pi r, but it's also integrating across this thickness r. So the dimensions of this is going to be 2 pi. So this area of this ring is going to be r and also 2 pi r. So that area is going to be the circumference, but it's also got this d theta. It's got this dr dimension to it too. All right. Well, now we got to solve for dq. dq is going to be equal to, we're going to multiply both sides by 2 pi r dr. Going to multiply sigma by 2 pi r dr, and what we're going to get is 2 pi sigma times the radius times the change in the radius, okay? Well, let's go ahead and evaluate what dv is. dv is going to be equal to dq over, well, it's going to be k dq over this distance from this point right to here, okay, which is going to be x over r radius squared. So it's the straight line distance. So in this case, it's going to be equal to x squared plus r squared. And then substituting in for our dq, which is 2 pi sigma r dr, what we're going to get is k times 2 pi sigma r dr all over the square root of x squared plus r squared. And now you've defined how you're going to approach this integral of dv. So how you're going to integrate dv. Let's go ahead and try it. Well, we're going to integrate dv, and we get the integral of the other side, which is going to be k times 2 pi r times sigma. Actually, let's redo that. 2 pi sigma r dr all over square root of x squared plus r squared. So now we have to think about what are our limits going to be. Well, this one's easy. It's going to it's going to go from VI to VF. And this, we're going to be starting at 0 right here, a 0 radius, and going out to a very far radius from 0 to capital R. And I'm just going to say this is from 0 to capital R right there. Okay? So let's go ahead and try this integral. Delta V is that part. And I'm going to bring my constants to the front. So I'm going to put 2 pi sigma times k in the front. And now I'm going to go ahead and go from 0 to R, capital R, and that's R dr over the square root of x squared plus r squared. Okay? And so now we're set up. So we're going to need more room to do this, but we'll come back to this and write our solution. Okay? So I'm going to copy this exact thing over to our whiteboard. Okay? And again, I'm going to come up to here, use a pen, begin writing our solution. So delta V is going to be equal to, and I already kind of lost what I'm writing, 2 pi sigma times k from 0 to R, and this is going to be small r dr over the square root of x squared plus r squared. Okay. So I recognize how to do this. This is a U substitution problem. So I'm going to set U equal to x squared plus r squared. And so I'm going to differentiate this with respect to r. So I'm going to differentiate this stuff with respect to r plus r squared with respect to r. And what you get is you get 2r to the first power. And so du is going to be equal to 2r dr. And so dr is going to be equal to, and let's make that look more like an r, is going to be equal to du over 2r. Well, now we're going to go ahead and substitute. We're going to go ahead and substitute u in for this bottom part, and we're going to substitute in dr into this top part. Okay? And now we're going to rewrite our integral, which is going to be 2 pi sigma times k from 0, well, again, we have to solve this integral independently because you can't just put in u's and start, because once you do that, your limits change. So let's just solve this independently. And I'm going to actually do it in red. So that means, so we're going to have our, actually I'm going to do this in black and just keep it consistent with everything that we're going to do. So what we're doing is we're substituting in our u's. So we got r, and dr is du over dr, du over, dr is du over 2r, I meant to say. And now we're going to substitute in u for our x squared plus r squared, and that is just u. Well, r's are going to be eliminated. This u to the square root of u, I'm going to actually call this du over 2 square root of u And this u, I'm going to bring up top and to the negative 1/2 power du. So now I'm going to integrate this. Okay, I'm going to bring the 1/2 to the front. U to the negative 1/2 power integrated is going to be u to the 1/2 power divided by 1/2, which is going to be 2 over 2. Oh, I forgot the c. Plus c. And this is going to then become, the 1/2 is going to come, the 2 is going to come to the top, so 2 divided by 2, u to the 1/2 power plus c, and that's just going to be equal to u to the 1/2 power plus c. Well, let's go ahead and use this to our solution. So delta v is going to be equal to, I'm going to copy our constants in front, 2 pi sigma times k. All right, and now we know this entire thing is just u to the 1/2 power, where u is x squared plus r squared. So that whole thing is just going to be x squared plus r squared, and it's u to the 1/2 power square root that we are evaluating from 0 to capital R. Okay. So I'm going to copy my constants again. Okay. And I'm going to put my r into this. So that's going to become x squared plus capital R squared. And now I'm going to put in my 0, which is just x squared plus 0 squared. Okay, which is going to work out to be 2 pi sigma k times the square root of x squared plus r squared minus square root of x squared. Or in other words, what we could write is 2 pi sigma times k x squared plus r squared plus, minus x. Okay? So let's switch back. So that means this whole thing is become 2 pi sigma k square root x squared plus r squared minus x. And that's our solution. As you can see in another book, this is the similar solution that they have, except they didn't choose to use k here. They put 4 pi epsilon naught, and 2 pi on top will take that out, and that'll just become 2. But it's the same solution that we just got. So essentially what you should have learned is you could actually take the sums of the little differentials, the little integrals of all of the little charges upon a continuum, and using gradient functions get minor little voltages for each one of those electric fields. So you could do the same thing that we just did, but now you'd use the if somebody gave you an electric field solution, you could differentiate that with respect to x, y, and z, depending on how many dimensions they give you, and that you could use this to actually get the voltage in the x direction, the voltage in the y direction, and the voltage in the z direction, right? So all they have to do is give you a solution for an electric field along those, I guess what I'm saying is, if you differentiate the voltage with respect to distance now you could get an electric field, okay? And you just have to solve it along one of these dimensions, okay? Related homework problems to this is going to be 5.10 and 5.11. So please try these out. Thank you.